Hey there, and welcome to This Explainer. I'm really glad you tuned in today. Go ahead and grab a comfortable seat, maybe a cup of tea, and let's just take a collective breath. Today, we're taking a relaxed, focused look at something we interact with literally every single day, but probably rarely think about, and that's water. Specifically, we're exploring the absolutely fascinating invisible chemistry of everyday water. If you're a college student currently staring down a daunting chemistry syllabus, or honestly just someone curious about the natural world, consider this a safe, low-pressure space to finally understand the whole concept of water hardness. We're going to break it all down simply, step by step, without any of the usual academic stress.
Okay, so let's dive right in. Water is often called the universal solvent. It's nature's most wonderful and abundant compound. But crazy enough, less than 1% of the world's water resources are actually available for our ready use. But what's truly amazing is water's journey. Long before it ever reaches your tap, it travels miles and miles over rocks, deep underground, and through rich soil. And because it's that universal solvent we mentioned, it doesn't travel alone. Along its journey, it picks up these microscopic souvenirs from the earth. So, the calm surface of the water we see, it actually hides this incredibly busy, invisible world of dissolved minerals.
So let's ground this in a really relatable everyday experience. Have you ever traveled to a different city, or maybe just moved into a new dorm or apartment, and noticed that your shower feels entirely different? You go to wash your hands or shampoo your hair, and instead of getting those big, fluffy bubbles you're used to, you end up with this weird, sticky, almost curd-like residue. It's incredibly frustrating, right? It feels like the soap is just broken. Well, it's not the soap. It's actually the water. And this perfectly illustrates the core difference between the two main types of water we interact with. First, we have soft water. Think of rainwater. Because it hasn't traveled through deep underground mineral deposits, it forms a soft, creamy lather with soap almost instantly. But then we have hard water, like the kind pumped from a deep bore well. This water gives us that sticky, curd-like residue and makes it so incredibly difficult to get clean. So your sensory memory isn't playing tricks on you. There's a fundamental physical difference in how these waters behave.
Which brings us to our first real topic, the great soap mystery.
To really understand the cause here, we need to look at what's actually happening in our sinks and showers when we turn on the tap. In chemistry, hardness isn't about the water feeling physically hard to the touch. It's actually literally defined as the soap-consuming capacity of water. It's a characteristic property that actively prevents the lathering of soap. When you use hard water, the water is effectively eating or consuming your soap way before that soap can actually do its job of cleaning your skin or your clothes. Wild, right?
So let's meet the microscopic culprits behind this.
Who exactly are these invisible hitchhikers that water picked up on its journey through the earth? Well, remember those souvenirs we talked about earlier? As water acts as a universal solvent, percolating through limestone and soil, it dissolves and holds specific microscopic minerals in solution. The two primary offenders here, the main culprits of hardness, are calcium ions and magnesium ions. And because these are dissolved on a molecular level, you simply cannot remove them by basic physical processes. Like you can't just run hard water through a standard paper filter or let it sit in a glass and wait for the hardness to settle at the bottom. The calcium and magnesium are deeply, securely locked into the water.
Now, take a look at the simple chemistry playing out here. Normal soap is usually made of sodium or potassium salts of fatty acids. The sodium part loves water and the fatty part loves oil and dirt, which is exactly how it cleans. But when soap meets hard water, the calcium and magnesium basically jump in and kick the sodium out. They literally replace it. The result is calcium stearate or magnesium stearate. And unlike normal soap, these new compounds are completely insoluble in water. They form that stubborn, white, curd-like precipitate that we commonly call scum. That right there is the sticky feeling on your hands.
Now don't let this overwhelm you because there are really only two types of hardness to remember.
Okay, if you're studying this for a class, take a deep breath. I know it might seem like there are endless chemical reactions to memorize, but you really only need to categorize these mineral souvenirs into two simple types. Think of this as your cheat sheet. The first type is temporary hardness. This is caused by the bicarbonates of calcium and magnesium. And the beautiful thing about temporary hardness is that it's super easy to defeat. You just boil the water. The heat breaks down the bicarbonates into insoluble carbonates that simply settle right at the bottom of your pot. But then we have the second type, which is permanent hardness. This one is caused by the chlorides and sulfates of calcium and magnesium. Boiling does absolutely nothing to these guys. To remove permanent hardness, we actually have to use external chemical treatments, like the lime soda process or ion exchange resins, to carefully coax those minerals out of the water.
Moving right along to our next section, measuring the invisible.
So we know what hardness is, and we know its two types.
But if you're an engineer or a chemist running a massive water treatment plant, you desperately need a universal language to measure the invisible. And that brings us to this incredibly friendly number, 100. Honestly, if there's just one thing you take away from the math side of this topic today, let it be this number. Because chemists, believe it or not, actually wanted to make these calculations as convenient and stress-free as humanly possible.
See, because water can contain a completely chaotic mix of magnesium chloride, calcium sulfate, and half a dozen other salts, trying to measure them all individually is a total nightmare. So chemists decided to convert all forms of hardness into a single unified standard, calcium carbonate equivalents, or CaCO3. Now, why calcium carbonate? Well, two major reasons. First, it's the most insoluble salt that precipitates out of water, which makes it a phenomenal benchmark. But the second and absolutely most important reason for us, its molecular weight is exactly 100. It makes all the multiplication and division involved in water analysis so incredibly easy. It's a universal standard designed purely for human convenience.
And once we've converted everything to our convenient calcium carbonate standard, we express it in standard units. The most common ones you'll see in a lab report or a local water quality website are parts per million, or ppm, and milligrams per liter, or mg per L. And hey, here's a great shortcut for you. In water chemistry, 1 ppm is exactly equal to 1 mg per L. They are literally the exact same thing. You might also run into some older units like degree Clark, which is used over in the UK based on gallons, or degree French. But honestly, just think of them simply as different dialects of the same straightforward measurement language.
Okay, so let's get down to it. Why hard water actually matters in the real world. Why do we care so much? Why do we spend millions and millions of dollars globally treating water? Well, on a domestic level, hard water is quite literally the enemy of cleaning. When doing laundry, that insoluble white precipitate we talked about earlier physically sticks to your fabric fibers, leaving your clothes feeling harsh, stiff, and scratchy, which actually significantly shortens their lifespan. When bathing, because that nice lather isn't forming, dirt gets trapped on your skin, and that curdy scum sticks right to your hair, leaving it feeling greasy and lifeless. And over in the kitchen, hot hard water releases its minerals directly onto your dishes, leaving those annoying white spots and actively degrading your glassware over time.
But as frustrating as bad hair days are, the industrial hazards of hard water are massive. In huge industries that rely on water boilers for steam generation, those calcium and magnesium salts precipitate out due to the extreme heat, forming these hard, rock-like limescale deposits right on the inside of the boilers. This scale acts as a stubborn insulator, which means industries can waste up to 25% of their energy just trying to heat the water through that thick scale. Plus, it clogs up pipes, leading to early structural breakdowns. And in extreme cases, the chemical reactions within the boiler can cause the metal to become super brittle, a highly dangerous phenomenon known as caustic embrittlement. That can literally lead to catastrophic equipment failure.
So, while we obviously spend a lot of time engineering solutions to soften water, using those lime soda processes or complex ion exchange resins we mentioned, it's really helpful to just step back and reframe how we look at it. Because hard water isn't a flaw in nature. It's simply a chemical record. It's literally the Earth's fingerprint left behind in the water. Every single ion of calcium or magnesium is a tiny testament to the incredible miles that water traveled underground just to reach you.
As we wrap up this explainer, I want to leave you with this final thought. The next time you turn on your tap, or even the next time you're frustrated by a lack of soap lather in the shower, take just a moment to appreciate the science happening right in front of you. You aren't just looking at water, you are interacting with dissolved mountains and subterranean caves. If a single drop of water carries the story of the Earth it touched, what invisible journeys are flowing through your home right now? Thank you so much for hanging out and learning with me today. Keep asking questions, definitely keep staying curious, and I'll catch you in the next explainer.